Okay, so thank you very much, and so let me start by thanking the organizers, Riddhi and Manju, for the invitation, and it's a real pleasure to be here. So I noticed that most of you are mathematicians, and I'm a physicist, so sometimes I'll be using notations and maybe terminology or jargon, which is physics jargon. So if you don't follow anything, please ask me. So this is a sort of recent work which was done in collaboration with my colleague Gregory Sher at LPTMS and Orsay, and we have a common graduate student, Bertrand Lacroix. So this work is actually motivated by a sort of current area of physics, which is called the cold atoms. And so what I'll do first is just give you a sort of overview of this cold atom physics, just very basic things. And then, just to say why we are interested and how these cold atom problems are related to random matrices that most of us are familiar with. So let me start with this sort of motivation. So okay, here's the outline of my talk. So I'll start with this, ultra-cold trapped fermions and tell you what are the questions and what people are interested in. And then I'll discuss an example in 1D system, where we'll see that essentially one can map the positions of free fermions in a 1D harmonic trap. I'll explain this in detail as I go on, to the eigenvalues of a Gaussian unitary ensemble. And so one of the questions was that is there any 2D cold atom system which can be mapped to, for example, in the 2D complex Ginibre ensemble, eigenvalues of complex Ginibre ensemble. And in fact, what I want to show you is that indeed, there is such a physical system. So this sort of provides a sort of physical realization of the complex Ginibre ensemble and even experimentally accessible. And that's what we found interesting about it. And then finally, if I have time, so I'll talk about two specific observables. So one is this so-called number variance or full counting statistics. And the other is called the Rényi entanglement entropy. So entanglement entropy is a sort of very hot topic in physics these days. And it's not always difficult to compute this quantity for a typical quantum system. And here we'll see that using this correspondence to complex Ginibre ensemble, one can calculate this entanglement entropy exactly for these free fermions in a 2D rotating harmonic trap. Okay, so that's the sort of program. And so let me start just by telling you what is ultra-cold trapped fermions. Okay. So this is a subject which has really become very, very sort of popular in physics these days. It got 3 or 4 Nobel Prizes in the last 10 years or something. And so main sort of big advances in this field is actually experimental manipulation. So they have these cold atoms, and so they can actually trap these cold atoms by putting a laser trap, and they can manipulate these atoms and basically see them. I'll show you some pictures. And so this actually allows you to sort of probe at the experimental level really the quantum and statistical fluctuations in these many body systems over a wide range of temperatures and other parameters. So there are these 4 basic features in these experiments. So one is that, okay, you have these atoms in a confining laser trap. And the second thing is that they can manipulate, they can create this laser trap in any dimension, 1, 2, 3. Not just 3-dimension, but you can make 2-dimensional trap, you can make 1-dimensional trap. So you can actually study the effects of dimensions. And also you can tune the interactions between atoms. So these are the atoms which are there in the space, and usually there's always some interaction between the atoms. But using something called phase-back resonance technique, they can actually tune these interactions and even make them non-interacting. So you can tune the interaction to 0. So you can study really these non-interacting atoms which fluctuate only because of quantum fluctuations. And so that's also, sort of great thing that they can actually study the effect of interactions basically, or no interaction. And then they can tune the temperature, effective temperature of the trap, as well as the number of atoms inside the trap. So this is also tunable. So there are many things, which can be done, which were not possible to do in traditional condensed matter systems, but in these cold atom systems is possible. And in fact, what you find is that there's interesting quantum many-body effects, even in absence of interaction. Just a few quantum particles, just because the quantum nature. By quantum nature, I mean that, for example, in bosons, you can have phenomenon like Bose-Einstein condensation, which means that many bosons can condense into the ground state of the system, of this many-body system, in absence of interaction, for example. Or the fermions. So fermions, they have this property which is called the Pauli exclusion principle, which means that you cannot put two fermions in the same state or same position in space. So that effectively it's a statistical nature of the fermions, and this sort of induces an effective repulsion between the fermions, even though there is no direct interaction between these fermions. We'll see this. So these are the sort of basic features of these cold atom systems, and we'll be mostly focusing on systems which are non-interacting, but they're quantum particles, okay? So in absence of interactions. So this is the sort of typical picture you have. So you have this laser trap, it's like a harmonic trap potential, and this is this space, and you have these red dots are like the atoms, basically. So first thing that happens is that they are actually confined in space because of this potential, they cannot go very far away. So they're confined in space, in a finite region of space. And so here is a picture from the experimental group of Greiner from Harvard University. So this is lithium-6 atoms, which are fermions, and this is two-dimensional fermion in a trap. And you can actually see these are really, you can image the positions of the fermions, and you can actually measure their fluctuations, for example. So you look at one particular area here, and you can count how many fermions are there, and what is their number variance, what is their full counting statistics, and all these things. So this really, many things you can, really image them and measure it, basically, okay? So now, the thing is that, what happens is that if you are near the trap center here, so you don't see the curvature of this potential. So it's more or less like a translational invariant system. So this is what is called the bulk, okay? So here, because there is no interaction, you can actually treat this problem in a sort of traditional Fermi liquid theory or many-body physics, which is translational invariant system, like local density, something called local density approximation or Thomas Fermi approximation, and so on. So many properties here, people already knew from condensed matter physics, 50 years back. You can actually probe here. Here the properties are actually independent of the, they do not see curvature, so you can do, there are many methods for that, okay? However, the problem is that because you have a confining trap, it's the system has a finite support, which means that there is a sort of edge here on both sides in this 1D example. And so what happens is that you cannot apply the traditional translational invariant many-body system near the edges. There's a translational invariance get broken. And here what happens is that the typical distance between the fermions becomes very large. So the number of them is also very small. So as a result, both the quantum and thermal fluctuations become very important. And the traditional methods do not work, okay? And in fact, this was sort of pointed out long time back from 1998 by none other than Walter Kohn, who is a Nobel laureate. He's a sort of father of chemistry in some sense. And they pointed out that this fact that the traditional starting point of density-based many-body theories in homogeneous systems is inappropriate near the electronic edges, okay? So how do we actually understand the correlations or the other properties near the edge? Because we cannot apply the usual traditional condensed matter theory. And so here what happened was in the last few, I'm not going to tell you in details, but so what happens is that it turns out that for this particular, let's say in the harmonic trap, in that case, what you can show is that the positions of these fermions in 1D, and I'll show that in a minute, they are actually exactly in one-to-one correspondence to the eigenvalues of a GUE, Gaussian unitary ensemble eigenvalues. And for the GUE, we know a lot of their edge properties, okay? So we know that this is Ayyer kernel and correlations and everything is known. It's a determinantal process. So using this one-to-one mapping, we can then use this RMT technique to study the edge properties, okay? So this has been our program for the last 3-4 years with several students and collaborators that we have been working on this system. And so you can see in this list, there's one mathematician that you may know, which is Neil O'Connell, and but mostly other physicists, and you can find a recent review that we wrote on this subject I'll just show you one example, but I'm just telling you exactly. So essentially, the point is that RMT was extremely useful, and it was a very good, nice application of RMT, which actually allowed us to probe the edge properties where the traditional techniques fell. Okay, so RMT was extremely useful for this particular physical system. Okay, so let me just show you, just illustrate this for just the 1D case and at 0 temperature. So I'm going to consider free fermions. I'll tell you exactly what I mean by that. Zero temperature in 1D harmonic trap, and I want to show you that you can map this exactly to the eigenvalues of a Gaussian unitary ensemble. So how does this mapping work? It's very simple actually. So let's think of first just one single electron. So I'm talking about quantum mechanics. I assume that most of you are familiar with quantum mechanics. If not, just think of this as a Hilbert space, and so you have the state vectors and you have an Hamiltonian operator, and so basically you are interested in the eigenvalues and eigenfunctions of this Hamiltonian operator. So for a single harmonic particle, this you have the textbook quantum mechanics. So in one dimension, so let's say I have a Hamiltonian which is p square by 2m. By p operator, I mean the momentum, which is just the grad basically. So minus h bar over I times grad. H bar is a Planck's constant, so it's essentially grad square, and so this is just Laplacian basically, and here you have this harmonic potential which is x. So when I have a hat, I mean the operator. So this is a Hamiltonian operator. So it's eigenvalues and eigenfunctions which are of interest to us. So they satisfy the Schrodinger equation where epsilon k are the eigenvalues, and phi kx is the eigenfunction in the real space, and it has to vanish at plus minus infinity. This is textbook quantum mechanics. And you can find these eigenfunctions explicitly. They're just given by Gaussian times these Hermite polynomials. Hermite polynomials are just orthonormal polynomials like this. And this constant alpha here is just square root of m omega by h bar. H bar is the Planck's constant. And the eigenvalues are quantized, k plus half h bar omega. So one thing to notice is that this fluctuation, so it means that the phi kx, so if I'm in the ground state, that means k equal to 0, lowest energy state, the states are quantized. In the ground state is just a pure Gaussian, and you have these fluctuations because of quantum mechanics, because if h bar was 0, okay, which means the classical physics, that means alpha is infinity, so then this thing just becomes a delta function in the ground state. So this is a classical particle. You know that particle is just has a delta function, it's just at a fixed position in space. But quantum mechanics tells us that no, it's never a delta function, there is a certain width to it, and the width is just specified by square root of m omega by h bar. Omega is the frequency of this trap. So this is our basic quantum mechanics, so everybody knows this, and these are Hermite polynomials. Okay, so now I'm going to consider not just one electron, one fermion, but you have n fermions. Okay? So which means that now my operator, Hn, total operator, is sum of the n operators, Hi, and each of the operators, the ith particle, has its own Hamiltonian, and the total Hamiltonian is sum of Hi. Note that here it's a non-interacting, because I do not have any cross terms here which connects two different fermions. So these are non-interacting fermions. Okay? So I want to now find out the eigenfunctions and eigenvalues of this many-body operator Hn. And how do you do that? So it's very simple. This is my goal, and in particular I'll be interested in the ground state wave function, which means at 0 temperature. So that means the Hn should be operating on some psi naught. Psi naught is a function of x1, x2, x3, xn, n coordinates. I have n particles on a line. And so what do I mean by fermion? So fermions means that this wave function, fermion simply means that it has to satisfy the Pauli exclusion principle, which means that this wave function must vanish whenever any two coordinates become equal. Okay? So this is the Pauli exclusion principle. So which means that it should be some antisymmetry combination such that whenever any two xi equal to xj for I not equal to j, this function should vanish. Okay? So how do we construct such a many-body ground state wave function? So it's very simple. So because there is no interaction term, so I can take the product of single particle wave functions. Okay, so phi 1. So for example, if I have two particles, I can take phi 1. So one particle in state 1 and the second particle in state 2. So this is, and my total Hamiltonian for two particles is just H1 plus H2. So clearly, I mean, this is, this guy here, by definition, if I operate by this Hamiltonian here, so this will give me, epsilon 1 plus epsilon 2 times, because they are independent, so. Okay. So this is clearly an eigenfunction of this H2 operator for the many-body operator with eigenvalue epsilon 1 plus epsilon 2. But it does not satisfy this antisymmetric property. So what you have to do is to construct the many-body state for these two particles thing, ground state, let's say, or not, for any state, in fact. So what you can do is just antisymmetrize it. So you write phi2x2 minus phi1x2, phi2x1. So both of them are actually eigenfunctions, so they are linear combinations. You can normalize it with some factor here. So this is going to be an eigenfunction of this H2 with eigenvalue epsilon 1 plus epsilon 2, because each term is an eigenfunction, and but it satisfies this antisymmetric property. Okay? So you have to antisymmetrize this wave function, and so the ground state wave function therefore would be for n particles. You just take n of them, okay, and you make the antisymmetric combination, which just becomes a determinant. And this determinant is called what is called the Slater determinant in physics. And this is n by n determinant. And inside the entries, I have to take the eigenfunctions that correspond to the, because I'm interested in the ground state, because the energy will be epsilon 1 plus epsilon 2 plus epsilon 3, etc. So the lowest energy state will be just putting the n fermions in the first n levels, essentially here. I cannot put two of them in the same level, clearly, because of this antisymmetric property. And so this is what is called the Slater determinant. And this is the ground state many-body wave function of this quantum system with the eigenvalue, which is the sum of these energies. So this is just n square over h by. Okay, so this is the very basic things. And this object here, it encodes the information about the quantum fluctuations in this many-body system. Okay. So now I can actually evaluate this ground state wave function explicitly, because you recall that the single particle wave functions were just Gaussian times Hermite polynomials. So when you calculate this determinant, the Gaussian term comes out of the determinant. And so what you have is determinant of just a Hermite polynomial. And determinant of any orthogonal polynomial, you can always bring it to a van der Waals form. For example, if you have just, three particles, so x1, x2, 1, 2, 3. So first h0 is 1, and then you have the 2x1, 2x2, 2x3, and then you have 4x1 square minus 2, 4x2 square minus 2, 4x3 square minus 2. So I can always, just taking linear combination of the rows and columns, I can just multiply by 2 and add to this, and essentially this will just become 8 times the van der Waals determinant. And the van der Waals is just a product of xi minus xj. Okay, so you can actually explicitly evaluate this, this ground state many-body wave function. And so in quantum mechanics, what is important is not just the wave function, but it's actually wave function absolute value square. And so this is a positive object, and it's totally normalized to 1 in the n-dimensional space. So you can interpret this as a sort of probability distribution function, PDF, of these n variables. So this is what is called the ground state wave function mod square. So this is like a joint distribution of the positions of the fermions in the ground state, that means lowest energy state. And you see that immediately that it has this form when you take the square. So there is this Gaussian and then van der Waals square. So this is, and this object, it means that it encodes the quantum fluctuations. There is no temperature here, there's zero temperature, so no thermal fluctuation. It's only because of quantum mechanics they are fluctuating. And so the quantum fluctuation is essentially completely governed. The joint distribution of the positions is exactly given by the GUE. So I just want to tell you, recall you to some of you forgotten probably, that the joint distribution, if I have taken n by n Gaussian unitary ensemble with normal entries, then the joint distribution is well known, and this is just given by, again, a Gaussian times a van der Waals square. And this is just a normalization constant here, normalized to 1. And what you see is that the ground state wave function square has exactly same form, and which means that the positions of the free fermions in a harmonic trap at 0 temperature behave statistically as the eigenvalues of a GUE random matrix. Again, the fluctuations here come from quantum mechanics. So you have this, equivalency in law that these positions up to this, trivial factor alpha, which are square root of m omega by h bar. So they are exactly equivalent in law to the joint distribution of the eigenvalues of a GUE matrix. Okay? So this mapping was actually very useful because we know that the GUE eigenvalues actually form a determinantal process, which means that any m-point correlation function, which is defined as taking the joint distribution and integrating out from m plus 1 to n, and okay, there's this normalization factor here. So this is the m-point correlation function. And what you can show is that you can always write this m-point correlation function as an m by n determinant with the entries, which remains the same for any m, that is, and entries are what is called the kernel, which is just this, take the single particle wave function, phi kx prime, and k equal to 0 to n minus 1. So the kernel is a central object for any determinantal process, which means that any m-point correlation, if I know this kernel, this is the basic building block, and then I can just construct determinant, higher and higher determinants out of this kernel, and that way you can actually calculate the correlation function. In the physics literature, this is what is called the Week's theorem in some sense, and this is just this basic idea of the determinantal process. Okay. And so, for instance, if I look at the 1-point function, which means just the average density of these positions of the fermions or position of eigenvalues of GUE. So this is just the kernel at the same point, k n xx, and this is just phi k mod x square. So it has this interpretation, like in the ground state, like each state up to 0 to n minus 1 occur with probability phi k mod x square with 1 over n, and so you can interpret this as a sort of putting each particle in at level 1 to n. Okay. So this is the object which goes to the Wigner's semicircular law. We all know this in the large n limit. Okay, so everything we know about the GUE eigenvalues because of this determinantal property. We know everything, all properties of this kernel. For example, at the so we know that the kernel in the bulk has this sine kernel form, and at the edge it has this airy kernel form. Okay, I'm not going to the details, but everything is we know about this GUE process. So we can actually then use this equivalence to make exact predictions for these cold atom systems, the positions of fermions in a 1D harmonic trap. As I said, the average density of fermions is given by the Wigner's semicircular law. Interestingly, people in the cold atom physics knew this density form, but nobody somehow made the connection that this is actually exactly Wigner's semicircular law. Okay, and similarly, from the local density approximation, people knew that there is a sine kernel in the bulk, but somehow this correspondence to the RMT was not known, and so they didn't know what are the edge properties, and you can show that this is exactly a kernel. And furthermore, if you look at the scale distribution, that is, you center and scale the position of the rightmost fermion, x max, in this 1D harmonic trap at 0 temperature, and then this is exactly described by the Tracy-Widom GUE, because this will correspond to the largest eigenvalue of a GUE matrix. Okay? So these are very standard things, and then the other things that you can do, as I said, square root of m omega by h bar. So omega is this frequency of the trap. Okay. So, and there are two other, interesting observables in the cold atom physics. As I said, number variance. So you take an interval minus L to plus L, and you just count how many fermions are there, and you can ask, okay, this is an object which is fluctuating again because of quantum fluctuations, and you can ask what is the variance or even the distribution of this number of particles inside this minus L to plus L. But this will be again given by the exactly number variance of the GUE, and we know everything about that. But there is one object which doesn't have a direct one-to-one, direct sort of meaning in the RMT literature, which is called the entanglement entropy, and I'll come back to that. which sort of measures this quantum correlation of this interval minus L to plus L with the outside of the subsystem. And we'll see that even this entanglement entropy you can write in terms of the objects that we are familiar with RMT. Okay, and I'll come back to this near the end of my talk. Okay, so you can find some of this review in this archive. Okay, so this is the 1D system. So one of the questions that we wanted to ask is what happens for free fermions in a 2D trap? Because in experiments you can also do 2D. And is there any random matrix ensemble corresponding to 2D case? Okay, so this was the can we sort of make similar one-to-one mapping to some random matrix ensemble? Now in 2D, I mean, a sort of most common and well-known random matrix ensemble is the so-called Ginibre ensemble. So, and I'll be just focusing on complex Ginibre ensemble. What does it mean? So you take a n by n matrix, and this is a complex entries, and they are real and independent, imaginary part both are independent Gaussian normal variables with zero mean and variance half. And then you can, if you look at the n eigenvalues, so they're all complex, and so once again, this system has been very well studied in the RMT literature. And in fact, what is known, the joint distribution of eigenvalues are known, and the joint distribution of eigenvalues is given by exponential minus zi mod square times again zj minus z mod zk mod square. Okay? So this is a well-known result again in the RMT literature, and furthermore, I mean, these eigenvalues, once again, they form a determinantal process. So we know everything, correlation functions and everything about this complex Ginibre ensemble. And so the question is there any sort of, 2D cold atom system which can be mapped somehow, whose ground state wave function mod square can be mapped to this Ginibre eigenvalues, okay? So that was the question we started out with. So just to remind you about some properties of the Ginibre ensemble. So this complex matrix, I mean, if you look at the eigenvalues, typically in the complex Z plane, so this is a typical relation, and what you see is that the eigenvalues for large n, they are concentrated on a disk with uniform distribution, 1 over pi, and the radius of this disk with this particular parameterization I've chosen is actually goes like square root of n for large n, okay? And here, by bulk, I would mean that, when the distance is of order 1 from the center, okay, here, and the edge means that when the z is very close to square root of n. Okay? So z is square root of n plus order 1. So this is the edge and this is the bulk. Okay? So this is a well-known thing. Yes?
What is the interparticle with the edge in this also?
So this is actually goes like 1 over square root of n. In the edge, I mean, in the edge, I mean, if I divide by square root of n, it's order 1 basically. That's what I mean.
So in 1D it goes as 1 over n power 1.
Yes, yes. But here in 2D, no, it's different.
Oh, is it just?
Yeah. Okay, so, all right, so this is, and many properties are known. I mean, for example, I mean, you can also know the distribution of the largest eigenvalue, which is just a Gumbel law and so on. And basically, it's a determinantal process. So you know the kernel exactly. And both bulk and edge properties are well studied. And so we know this literature there very much. Okay. So the question is there any 2D trapped fermion system whose ground state wave function modulus square would correspond exactly to this joint distribution? Okay. So this is a question. Okay. Can we find a quantum system, that means a quantum Hamiltonian, whose many-body wave function mod square in the ground state would exactly correspond, just as we did in the 1D case. Okay? So this was the question we started out with. So one obvious choice, I mean natural candidate basically, would be to see what happens if I just take the same harmonic oscillator problem, but now my potential is 2D potential. That means half m omega square x square plus y square, E of xy. So I take exactly same harmonic oscillator problem, but now just the potential is 2D. And this is just a kinetic energy operator. So it's a Laplacian square. So if I take this problem, okay, so again, this is a non-interacting problem. So I can actually construct the ground state wave function by solving the single particle problem. So single particle problem, now again, x and y coordinates are separable. So the single particle wave function for a single particle with coordinates x, y in the 2D plane So this is just the product of the 1D wave function. So Hermite polynomial, same with index n1 and n2, and then e to the power minus alpha square x square plus y square. And n1 and n2 are positive integers basically. And the energy of this single particle, these things of that state is n1 plus n2 plus 1 times h bar omega. So this is my single particle problem, and from this I can write down this later determinant in principle and try to construct the many body ground state wave function. Okay. So this n1, n2, so it's a 2D plane basically in the n1, n2 both quantum numbers. And so I want to construct this later determinant, okay, just taking capital N of them and lowest one, and then just anti-symmetrize them. Okay. But if you do this, you can do this computation. So it turns out that this is a determinantal process again, and but this does not correspond to the joint distribution of Ginibre. It's much more complicated here. Okay. So even though it's a determinantal process, but it's not Ginibre. We wanted to find something close to Ginibre. Okay. So for instance, I mean, just to show you some picture for this process that is 2D harmonic oscillator. So in fact, we have studied this analytically, I mean, both for the bulk and edge properties. So for instance, the average density of the fermions is actually a cap. This rho n r goes like r, some constant square minus r square. So remember in 1D, it was harmonic oscillator, it was a square root here, because of Wigner's semicircular law. But here it's just a power 1. And here, the edge goes like n to the power 1/4, which is not the same as in the Ginibre case is order 1 actually. Okay. Yeah, but you can work in the radial coordinates also, right? So yeah, it's not completely obvious to show that this is circularly symmetric. Okay, but you can, I mean, if you work in the radial coordinates, you can show that it's actually okay, because the combination is such that it actually restores the circular symmetry. Okay, the density. Okay, so, but I'm not, not want to talk. So this it doesn't satisfy the bill basically. So we are looking for something, some quantum system which has this joint distribution of Ginibre. So what should I do? How should I modify this potential here to get this? Okay, so that was the question. So it turns out now, and this is the sort of main this thing of the talk, is that what you have to do is to take this harmonic trap in 2D. But now you just rotate it, this trap, with a frequency omega. Okay? And this is an experimentally realizable system, I'll show you in a minute. And so you just take this trap, and the experimentalists can do that. You make this laser trap, and you can just rotate this trap with a constant frequency omega. What that means, that the single particle Hamiltonian now just becomes as before. Okay, so this is just the kinetic and potential energy for a static trap. But there is an additional term which comes from what is called the angular momentum of this thing. So if you go into the rotating frame, then you get this additional term, which is just this angular momentum term. Okay? So this Lz is the angular momentum operator. Okay? And you have to set this capital omega to be less than the frequency omega of this trap in order that the fermions are confined. Because if capital omega is bigger than little omega, they just fly away. So the system is not confined. Okay? So you take this system, and then you can actually rewrite this Hamiltonian, this single particle Hamiltonian, just by taking a square and just rewrite as P minus m omega z cross r. This is a vector product square plus little omega minus capital omega times angular momentum operator. So this is the z component direction. So why do I rewrite this Hamiltonian in this way? Because now you can check the two limits. Okay, so first limit is when capital omega is 0, if this is static trap, not rotating one, then this is the previous problem that we just talked about. Okay, so this is a 2D harmonic trap, and it's not Ginibre. Okay. Now, the other limit is when you put the little omega equal to capital omega, the upper limit. Okay, so then this angular momentum term disappears here, and you just have this P minus this product square, and this Hamiltonian is what is called the Landau problem in physics. So it's like when you put a magnetic field perpendicular to the two-dimensional plane with this and this constant c, which is called the cyclotron frequency. And so if you put this magnetic field and you look at the electrons inside this magnetic field, and you have to solve, this is just a vector potential term essentially. This is the curl of A A square, this vector potential. In the symmetric gauge, if you write down, then this problem is exactly equivalent to, so if I didn't have this term, then this is exactly equivalent to a 2D electron in a 2D magnetic field, perpendicular magnetic field. Okay? So this problem has been very well studied, and in physics literature, it's called the Landau problem. Okay? So this Hamiltonian somehow it interpolates between these two limits. So one is a static harmonic oscillator, and the other is this this Landau problem. Okay, and so it turns out that you can actually diagonalize this Hamiltonian exactly, and so I want to look for the single particles wave function phi of xy. So I go into the coordinates z x plus iy and z bar x minus iy. And then you can write down the wave function, single particle wave function exactly. And this is just, okay, up to a normalization constant. This is e to the power half z bar, and you have this, n to the power n operators times e to the power minus z bar. And the eigenvalues are precisely given by omega minus capital omega times n1, omega plus capital omega times n2. And n1 and n2 are still integers. So you can diagonalize, and this is a single particle problem is well solved. And so when little omega equal to capital omega, then you don't have this term here, okay? Which means that the lowest, that is N2 is what is called the Landau level, okay? It's sort of this, N2 is like the Landau level. So again, you think of, okay, I'll show you a picture in a minute, but this is like N1 and this is N2. So these points here, integer points, so they are the different states, single particle states. Each point represents the single particle states. And if little omega equal to capital omega, the upper limit, so then this is the Landau limit. So there you don't have this term here. So that means the energy depends only on one quantum number n2, but it's independent of n1. Okay? So all of them have the same energy. So it's infinitely degenerate. So lowest energy state, which corresponds to n2 equal to 0, it's infinitely degenerate. Okay, so this is called the lowest Landau level. And but when you put this frequency capital omega, it breaks this degeneracy, because now these levels here, they look like this. So this is the n1, this is the n2, and these are the n2 equal to 0 level. This is the n2 equal to 1 level, n2 equal to 2 level, and now they have different energies because this term is there. So what did I gain by this? So this is our single particle spectrum, and now I'm going to put n particles, and I want to construct this ground state basically. Okay. So as I said, if you put capital omega equal to little omega, this just becomes a flat, so infinitely degenerate, and then the ground state is there can be many possible ground states, but you can construct any sort of ground states later determined out of the states. But when you put this frequency, so this degeneracy is lifted, so there's a unique ground state, and so you can just put the particles in the first n levels here, okay, and of course you have to make sure that they are in the lowest Landau level. So the highest occupied the particle in the level in this set must be lower than this guy, and this gives you a sort of bound. It says that if your capital, frequency of the rotating trap lies between these two limits, then your ground state is unique, and you can actually compute exactly this ground state wave function. Okay? And as I said, these things actually is possible. So just to show you, I'm just, this is a sort of experimental paper from the group of Eric Kernel, who got the Nobel Prize in cold atom physics recently, and they can actually, okay, this is a bosonic system, but they can do experiments with fermions also, and they can really study, probe the system near this lowest Landau level, basically. Okay, so we restrict ourselves in this range so that we have a unique ground state, and so this ground state corresponds to n2 equal to 0. So I'm in this first Landau level, and n1 I choose to be 0, 1 to n minus 1. So in that case, single particle states are actually, there should be n1 here. So it depends only on n1 because n2 equal to 0, and I take the first n1 of them. So again, it is of this form, that Gaussian times some polynomial, monic polynomial of degree n1. And so we can construct this later determinant exactly in the same way as before. and stator determinant just becomes Gaussian times the Vandermonde. Okay. So that means that in this problem, if I take my rotating trap between these two limits, I can calculate the wave function mod square. So that is exactly given by the joint distribution of the Ginibre eigenvalues. Okay. So this is actually a sort of very nice physical realization of the Ginibre ensemble, which has been around for a very long time. But I mean, now we know that you can actually realize it in a real experimental situation. Okay, so we have this, and the nice thing with this, so therefore we have a quantum system for which again we can just borrow the properties from the RMT literature to make exact predictions of this quantum system, which is, as I said, experimentally realizable. Okay? So this is the sort of main sort of message of this talk. I mean, that the 2D harmonic trap with rotating with a frequency capital omega, which lies in this range, then in its ground state is unique, and in this ground state, this is just a physical relation of the Ginibre. Okay, so this is so far. So let me just illustrate to you that what can we say. So Ginibre eigenvalues, I mean, they form, as I said, a determinantal process with this following kernel here. Kernel, remember, for determinantal process, kernel is a central object. If we know the kernel, you can calculate all the correlation functions in the bulk as well as at the edges. And okay, there are many people who have worked on that, including Manjunath and many others in the audience. And so basically, we can make exact predictions of this fermion system, both at the bulk and the edge, in a ground state using this Ginibre properties. But in addition, what we are able to do is to actually compute explicitly these full counting statistics as the number variance, and also this Rényi entanglement entropy, which is not a natural observable in RMT. But using this one-to-one mapping, you can actually, there are very few quantum systems for which you can calculate the entanglement entropy. I'll define it in a minute. And but here, using this correspondence, we can actually exactly compute this. Okay, so this is sort of main point of this. Okay, so let me just remind you what is entanglement entropy and number variance. What do I mean by that exactly? So okay, it's not a very, I mean, sort of intuitive concept at this moment, but okay, I'll just again go back to the just for illustration purpose, just 1D system. But I mean, you can immediately generalize to any 2D or other systems. Okay. So what's the general setting? So I have n free fermions again. That's my general setting. I'm at the ground state. His temperature is 0 in some confining trap. It can be any arbitrary trap, an arbitrary dimension. So I have a ground state, and this I'm using this quantum mechanical Dirac notation. So psi 0 is the many-body ground state wave function. And you can actually, from this, you can construct this density matrix, and this is the pure state, which means that the density matrix is just this operator here, psi 0, psi 0. Okay. Now, if you know this density matrix, then this is the full density matrix, and then many properties you can compute. I mean, this is just a useful for computation problem. Okay. So now imagine that you take a subsystem of interval A. Okay. It doesn't have to be central, I mean a center. You take any subsystem, and this is full system. Okay. So some domain basically. In 2D, it will be some domain. So now, number variance means what? So number variance means that I just look at the total number of fermions. I'm talking about fermions for the moment. Okay. The total number of fermions inside this interval. So this is a number operator, and so this is the total number of fermions. And you take this ground state and you look at the expectation value of NA square. So this is like a minus the mean square. So this is just the variance. Okay. So it just counts how what is the fluctuation of the number of fermions inside this subinterval A, because they can go out and come back in. Okay. Now, what is Rényi entropy? This is a much less intuitive thing. So entanglement entropy, I mean, roughly speaking, I don't have time to go through explain to you what is really entanglement entropy. But roughly speaking, entanglement entropy means that it's a quantum correlation between a subsystem A and its complement outside. Okay. Because classically there is no such long distance correlation, but quantum mechanics, because your states is all these things are entangled, single particle states. So there is some kind of quantum correlation or information that is available for the outside of the system, even though you focus only on your subsystem A. By measuring locally here, you can say something about outside. So entanglement entropy is just a measure of these quantum correlations, and formally the way you define it is the following. So you take your full density matrix rho, and you trace out the degrees of freedom which are outside the A, that is A bar. Okay? So this is called the reduced density matrix of the subsystem A. And once you have this reduced density matrix, then the Rényi entanglement entropy, which is, there is a parameter Q here, and so this is just a log of the trace of rho A to the power Q divided by 1 minus Q. In the limit when Q goes to 1, this reduces to the normal von Neumann entropy, which is the trace of rho A log rho A. So this is why this particular measure, I don't have time to explain, but you can take this as an operating definition of entanglement entropy. Okay? So let's see how it works now. So for instance, if we take our N fermions in a potential, so ground state wave function in the basis in a position space is just a Slater determinant with these eigenvalues, and we want to compute these two objects. So how do you go about it? Okay, so I have to go fast now. So the operational way of doing it is the following. So what you do is you take these single particle states, you have up n of them, okay, and you take this phi m star square, phi nx dx, integrate over x only over the subsystem A. So this defines a matrix, right? So it's a matrix n by n matrix. I have these n fermions, and this is called the overlap matrix, okay. So if this interval A was the full space, then by orthogonality, this will be an identity matrix. Okay? But because your subsystem A is is a subdomain basically. So this is non-zero, the element. So this is a non-trivial matrix, and this is called the overlap matrix. Okay? And you can show that this overlap matrix has n real eigenvalues, which are called little an, which lie between 0 and 1. So when they become identity matrix, if this length A becomes infinite, then of course all the eigenvalues become 1, okay, because it's identity. Otherwise they spread between 0 and 1. So what do I do with this? If you give me this overlap matrix, okay, so for any system, you just calculate the single particle wave functions and you construct this overlap matrix, and this is how they do it numerically, for instance, okay, overlap matrix, and then what you can show is that the variance of this number of fermions here in the ground state is given by the trace of this operator A into I minus A, which is just, so if you know the eigenvalues An, so this is a simple formula, An times 1 minus An, okay. And the Rényi entanglement entropy, similarly, this is I'm not showing you the proof of this, but this is well known, and this is actually given by the log of An to the power Q plus 1 minus An to the power Q. So for any quantum system, non-interacting system in the ground state, you first find out the single particle wave functions and just construct this overlap matrix and diagonalize it and get the eigenvalues. And if you know the eigenvalues, then so numerically this is how people do it. You diagonalize the eigenvalues and then you just do this sum, basically. This is how you actually calculate these two objects. Okay. So now, what are these eigenvalues An? What do I mean in the RMT language? Okay. So the point is that now, if you have a determinantal process, so you have this kernel K, right, for our determinantal process, and then what you can show is that if I take this kernel and if I project this x and y coordinates to this subinterval A, okay, so I just multiplied by the indicator function, then this projected kernel is an integral operator. So you can actually ask what are the eigenvalues and eigenfunctions of this integral operator. Okay? So this is just a Fredholm equation, basically, space. And the spectrum of this kernel, okay, this is I denote by A lambda. So this is infinite dimensional matrix, if you like. So the non-zero eigenvalues of that, you can show that this is exactly coincides with the non-zero eigenvalues of this operator overlap matrix A. Okay. So this is the relation. So that means the variance of NA I can write in terms of the overlap matrix, but I can also write in terms of the kernel as a trace of Ka into I minus K for a determinantal process. And similarly, entanglement entropy, I can write it as this object. So you see that this is not a very natural observable in the RMT language, but with this fermion correspondence, So this is exactly the Rényi entanglement entropy. I mean, normally in RMT you wouldn't calculate this, okay. So now the point is, for a deterministic process, we know, I mean, a lot about this kernel, so we can try to compute these things for number variance and Rényi entropy. Of course, the problem is that, to solve this Fredholm equation is not always easy to find the eigenvalues. For example, in the 1D case, where for the GUE eigenvalues, we do not know explicitly all the eigenvalues here, okay. But the advantage of this 2D Ginibre ensemble is that we can calculate these eigenvalues explicitly, okay, because of the circular symmetry. Okay, so there is another sort of reason why people study the entanglement entropy variance, because it's known in the physics literature that if you take an infinite, free fermion system without any trap, without any potential, just a non-interacting free fermion system, no matter which dimension you are, if you calculate the Rényi entanglement entropy of any subsystem A, and if you calculate the variance, they are exactly proportional to each other with a universal proportionality constant, which is given by pi square. No matter what the size of the subsystem or the shape of the subsystem is, this is an universal relation, conjectured relation in the physics literature. Okay? So this is this universal constant here. Now the question is, I mean, does this proportionality remain valid when you put the trap, or if you have a finite system of size, I mean, n number of particles? Okay? And this was the sort of question why we're interested in these two observables. Okay? So what happens to this proportionality for finite and trapped Fermi gas with an edge? So in the 1D system, we knew that this proportionality doesn't hold near the edge. It holds only in the bulk, but when you go to the edge of the system, then this proportionality breaks down, actually. Okay. But 1D system, it's still, we cannot calculate the entanglement explicitly because we do not know what the eigenvalues of the Fredholm operator are. Okay. But as I said, for the 2D case, we can actually compute, and I just show this result and then I'll stop. So why can we calculate this in 2D? The reason is very simple. So I take this 2D Ginibre ensemble, and I take my subsystem to be circular of radius r, circular disk of radius r. So I want to know what is the number variance of this number of eigenvalues here, which is the same as the number of fermions in this rotating trap. And I also want to know what is the entanglement entropy of the subsystem with the rest of the outside system. So you see this overlap matrix, okay, which is just a single particle states here, but integrated over this circular domain. Okay? But as I said, eigenfunctions are just z to the power n times exponential minus mod z square by 2. So if I just take this dot product here, because of and go to the polar coordinates, then you see that there is a phase e to the power I n theta, and there will be e to the power minus I m theta, and when I integrate from 0 to 2 pi, they become just orthogonal, okay? So which means that because the circular symmetry of the subdomain, this overlap matrix, or equivalently the kernel, is exactly diagonal matrix with diagonal eigenvalues, these eigenvalues an, which are explicitly, you can compute this just a radial part, just a incomplete gamma function. Okay. So we know explicitly these eigenvalues, so as a result we can then compute both Rényi entanglement entropy as well as the number variance. So I'll just show you the result. I mean, so basically this formula, we know these things explicitly. We just put it in this formula and do the asymptotics for large n. Okay, so so what do you get? So this is the variance. So I'm looking at the variance as a function of the scale distance r over root n. R is just the radius of this circular domain. So as r increases, so when r is of order 1, when you are in the deep bulk, this regime, so this is some non-trivial function of, which is given in terms of, order 1 function, which is explicitly given by this infinite sum. And then it just becomes a linear. So the variance is actually increasing as you increase this radius of this r. It increases linearly with a prefactor 1 over root pi exactly. So this is in the extended bulk when r is between root n and 0. And then when you go to the edge, the variance actually falls here. And falls very rapidly, and there is a scaling function, and you can compute the scaling function explicitly, which is given by this. Okay? So this is the picture for the variance. Okay? Why does it fall? Because when you go r becomes this, there are hardly any eigenvalues outside. So if you take the subsystem to be bigger than the natural Ginibre disk, there is hardly any variance there, fluctuation. So that's why it rapidly goes down. But what is nice is that you can actually compute this, the scaling function exactly at the edge. And the variance, again, we can just substitute, and it has, entanglement entropy. So for Q, it has this similar, very similar behavior. So what you find is that again in the deep bulk, it's a non-trivial function. Yeah, I just finished in 5 minutes. And then again here, it's a linear in the extended bulk with a prefactor, which is now given by some non-trivial Q-dependent number. And then again, the edge scaling is given by some other scaling function here. So you can compute this explicitly in the large N limit. And so what you see is that that there are 3 regimes. There's this deep bulk, there's this extended bulk, and then there's this edge regime. And in this extended bulk, if you look at the ratio of the entanglement entropy by variance, it's flat, as predicted, conjectured basically, I mean in general, for the free fermion system. But here it holds only in this extended bulk, but it fails both in the deep bulk as well as at the edge. Okay? And so this is this, so the proportionality sort of breaks down in this trapped fermion system. These two objects are not, and there's a lot of emphasis in the physics literature on these two, on this proportionality, because you see this Rényi entanglement entropy is not something that is easy to compute. Measure, for example, experimentally, or even numerically. So, but number variance on the other hand is a very physical object. You can actually measure it, and you can. So, if they are proportional, gives you one way to measure the entanglement entropy. But you see that it's not always true. I mean, it's true for free fermions in an infinite system. But if you have a trap or if you have a finite n, certainly it's valid in some regime, but not everywhere. Okay, so you have to be careful with that. Okay, so that's the sort of main conclusion. So let me just summarize. So the point is that there is an exact one-to-one mapping between the ground state of the free fermions in a 2D rotating trap in this frequency range and the eigenvalues of the complex Ginibre ensemble. And this sort of provides a physical relation of the Ginibre ensemble, complex Ginibre ensemble. And you can use the known results from here to compute exact correlation functions in the bulk and edge, as well as these two observables, number variance and Rényi entanglement entropy. And as I said, this proportionality between these two holds only in the extended bulk, but not everywhere. Okay, so you have to be careful in taking this seriously. And you can also compute the higher moments also of NR for the full distribution, full counting statistic. And so the main point is that there is an exactly solvable 2D quantum system for any entanglement. As I said, it's not easy to compute this entanglement entropy for a quantum system. But here we have an exact system where you can compute it for arbitrary n. And so let me sort of thank my collaborators. So there's a student, Basu, who did this work, and also the other students who have been working on this. And there are my collaborators on this subject. And so I think with that I'll finish. Thank you very much.